So, I mean, this presentation was originally supposed to be about Ethereum, but one little known fact about me is that sometimes I really hate talking about Ethereum. You know why? Like, there's times when I say some interesting thing on Twitter, like I say some cool fact about prime numbers that I just recently discovered, or link to some article about economics, and the top 5 replies on Twitter that I get are, "Hey, when ETH go up to 3,000? When Casper? When sharding? When is my Lambo sharded?" And I'm like, "Durr, do you not understand? Like, this is ultimately this is not about Ethereum, right? Like this is about enabling and like platforms of like open and global like human economic coordination and trust minimization and like censorship resistance and decentralization and like all of these other goals that we actually care about. And like every single blockchain that we're building is ultimately a means to that end. So why are these people on Twitter surprised when I sometimes express that I care about these ends and not just, like when the Lambo's going to be shorted to 900. So anyway, blockchains and trade-offs. So this is the blockchain-related presentation, but definitely more general than Ethereum that I'm going to be giving today. So first of all, blockchains by themselves are a far less efficient computer and database than technologies that have existed for over 40 years. Right, so if you want to talk about what blockchains are for, the answer is clearly not like simple raw efficiency. And there's a few examples of this, right? So if you look at Amazon EC2 pricing, if you look at, let's say, a medium size general purpose computing, the cost of this is about $0.04 per hour. Now, let's look at pricing of the Ethereum world computer. So how much does it cost to make the Ethereum world computer do stuff for you? Well, every Ethereum block, which comes every 14 seconds, on average takes about 200 milliseconds for my laptop to process. So let's call a block 200 milliseconds of CPU equivalent time. A block has 8 million gas, and let's assume an average gas price of 4 gwei, which is roughly what you can get over the last month or so. Let's assume the price of Ether is at 420, multiply all of those things together, and the cost of filling an Ethereum block is $13.4. $13.4 for 200 milliseconds, on the Ethereum world computer, 4 cents for an hour of Amazon EC2. That is a 1.04 million factor difference in efficiency. And so the Ethereum blockchain has about 1.04 million x overhead compared to Amazon EC2. Another way to look at it is this. Ethereum network size, 15,000 nodes. Safety factor. So safety factor, basically the block interval, so the 14 seconds between blocks divided by the block verification time. 14 seconds divided by 200 milliseconds, about 70. So a node in the Ethereum network spends about 1/70 of its time actually doing computation, and this kind of fairly large safety factor is needed for reasons like keeping uncle rates down, having a buffer in case some attacker figures out some way to do a denial of service attack, and like various other considerations. And the net overhead, if you multiply the network size, so everything gets processed 15,000 times, multiplied by the safety factor, 1.05 million. Storage. So you can get a computer, 250 gigabytes solid state drive for $80. On the Ethereum world computer, you can fill 1 byte of contracts data, which which costs you about 200 gas. So that at a 4 gwei gas price, and assuming Ether is at $420, that gives you $84 million for 250 gigabytes. 1.05 million factor overhead. By the way, these numbers all ended up being like almost exactly 1 million. Is like a total coincidence, and it's amazing. So the Ethereum world computer is 1 million times less efficient than regular computers. So clearly, raw execution efficiency is not what blockchains give you. So what do we want to get out of our blockchains in return for the efficiency costs and the other costs that we're paying in order to run things on blockchains? So here are some examples of goals that we talk about a lot. Right? So one is censorship resistance. Censorship resistance basically means resistance to third-party interference. So resistance to your transactions being interfered with by governments, resistance to your activities being interfered with by banks and payment processors, internet companies, resistance to you opening up like some Twitter feed and then Twitter suddenly deciding that it doesn't like your Twitter feed anymore. So like resistance to your products being, or your attempt to sell some products being shut down by banks and payment processors, even if your product is completely legal because banks and payment processors are chicken. All censorship resistance. Fraud resistance. So fraud resistance is first-party interference resistance, right? So instead of interference by third parties, not you and not people you're interacting with, here this is interference by the person you're interacting with. Why do they want to interfere with their own relationship with you? Well, possibly because they want to steal your money. Right, so some of the best examples of this are quite ironically inside of the crypto space itself, right? So you have Mt. Gox, which very famously blew up in 2014 and stole $500 million of people's money, despite the fact that Mt. Gox was built on top of decentralized cryptocurrencies. Mt. Gox was able to get away with stealing so much because it was a friggin' centralized trusted system run by a guy and company which proves to be absolutely untrustworthy. Exit scams, various different kinds of scams. So that's fraud resistance. Transparency. So perhaps you just want certain kinds of interactions to be on top of a platform where that platform is all those interactions are visible, and there's common knowledge that those interactions are visible. So everyone can see what's going on, and everyone can be sure that the things that seem to be going on are the complete set of things that actually are going on. Robustness. So you might want your service to not just randomly go offline in case one particular computer fails for some reason. And interoperability. So the Ethereum contract ABI is actually one of the most successful fully open APIs available in that particular way, right? Like anyone can launch a contract, and once they launch a contract, anyone else can programmatically call that contract and interact with it. Right, like the system is designed on top of high levels of interoperability, interoperable ABIs from the ground up. Cross-blockchain interoperability. Anyone can make an interoperability bridge between one blockchain and another blockchain, and this includes permissionless interoperability. So one of the reasons why is there are some developers who dislike quote platforms like things like Facebook and Twitter, is that they often have very kind of capricious and rapidly changing opinions about what kinds of third-party services it's okay to build on top of their platform. Sometimes there were developers that built entire businesses on top of Facebook and Twitter, and then Facebook just suddenly decided, we're just going to shut that API option down and we're going to build the thing ourselves. And the people's entire businesses were just destroyed overnight because of one particular decision made by King Zuckerberg or whatever other king of the internet at that particular time. So permissionless interoperability. You can design systems that interoperate with other applications, regardless of whether or not those other applications actively cooperate, and in fact, regardless of whether or not developers of those other applications even want you to interoperate with them, whether now or at some particular future point in time. So basically, all of this is kind of like different forms of monopoly lock-in resistance, which I think is a goal that people are increasingly caring about, especially as things like the monopoly power of social media networks becomes an increasingly hot issue in our society. So those are some goals. Now here's one problem. With efficiency losses as high as blockchains are right now, with efficiency losses of a factor of 1 million, the only applications that really need one of the benefits that I described are going to be willing to use public blockchains. So you can think of the utility of blockchains as being this kind of curve, right? Where the horizontal axis of the curve is the number of beneficiaries, the number of users, the amount of economic activity, the wideness of the adoption that some particular use case can reach. And the y-axis is either benefit per user or possibly even benefit per transaction, benefit per unit of usage of the blockchain. So on the left side, you have activities that reach only a very small number of users, but where the benefit per user is really, really high. But then you also have this big, long tail of use cases where the value of using a blockchain per each individual user, per each individual transaction, per each individual unit of economic interaction is smaller, but you really make up for it in volume. And the problem is that if you have a blockchain where using the blockchain is that extremely expensive, then I mean, right now it's okay, but in the long term, it's not going to be, the inefficiency could increase. It could go up from a 1 million factor inefficiency to a 10 million factor inefficiency, or to a 100 million factor inefficiency. And if things go in that direction, then basically the only usages that will be willing to pay for the blockchain are things that are that need the blockchain so much that they are just willing to pay the crazy high fees no matter what they are. What are those use cases? Basically cryptocurrency speculation and Silk Road. So this, if we want blockchains to really reach wider scale usage and really affects, things like improving the lives of refugees, giving identity to the poor, connecting together, providing for new kinds of economic interaction, letting people do, various kinds of economic agreements, crowdfunding type of things, issuing their own community currencies on blockchains. And if we want, even just regular plain old payments and buying, and buying coffees, if we want this much larger set of economic activity and the kind of full potential of things that people believe blockchains can, could eventually be used for, that affects the needs of, a much larger set of normal people to be usable, then I would claim the fact is blockchains just do needs to be cheaper, full stop. And this is probably reason number one why I believe scalability is just so super important. So imagine a blockchain that uses sharding, plasma, channels, whatever technologies to not to have only 1000x less execution efficiency, so only a 1000 factor overhead compared to doing things on centralized services. So we've gone down from a 1 million factor inefficiency to a 1000 factor inefficiency. Now you might say, well, that's still absurdly inefficient. Why would you even use this system? Well, programming languages. Running code in Python is 100, and executing code that's written in Python is 100 times slower than executing the same code that's written in C. How many people here have written a program in Python? How many people here have written a program in C? About the same, possibly a bit more on the Python. So clearly, people are willing to take very substantial losses in raw execution efficiency because they value other things. In Python's case, the thing that they value is basically simplicity of development. In the case of blockchains, well, I just gave you the list of things that why people might want to value blockchains, even if there is a 1000 factor overhead. And one of the key insights here is that you don't need to use blockchains for everything, right? Like chances are with your application, the vast majority of the computation is not going to be some kind of computation that needs to be run inside of consensus. Chances are it's going to be, there's going to be some vast majority of the computation that really could be done in some way, either client-side by individual users or through some system that's somehow connected to a blockchain, or it's part of the user interface, but it does not need to be done by every single node in a network. Now, there is going to be some kind of business logic core that does need to be run in consensus, but chances are it's pretty small. And if you multiply the cost of that by 1000, well, chances are it's not even necessarily that big a deal. So, other problems with public blockchains. Public blockchains have issues other than execution efficiency. One of them is latency. 200 milliseconds with a centralized service, 14 seconds to get one confirmation on Ethereum, and an expected roughly 33 minutes to get finality in the first version of Ethereum's Casper proof-of-stake system. Much less privacy, all the data is public, and different kinds of security risks. If you lose your money, you can't call mom to get your money back. Your money is really gone. So what kinds of approaches can we use to try to alleviate some of these issues, right? So one example of a really cool kind of category of technologies is layer 2 scaling. And I came up with this really interesting definition that probably covers, the entire class of this type of layer 2 scaling solution, which basically is that we can use a few transactions initially on-chain and set up some system of contracts. These contracts store assets, and these contracts implement games, like games as in game theory, where the expected outcome of the game, it depends on what messages that players could send in the future, but where the expected outcome of the game can be changed at any point by individuals sending purely or mostly off-chain messages. So we do a bit of on-chain activity. We set up this game, and this game might be some kind of interactive game between multiple participants. And basically, depending on what messages the different participants are capable of sending into the blockchain, that depends on the eventual outcome in terms of who the assets go to. Well, the game can be changed by individual participants in this game voluntarily signing, cryptographically signing off-chain messages and broadcasting them to other participants. And the broadcast, even though the broadcast and signing of the message is purely an off-chain operation, its mere existence affects and possibly significantly changes the expected outcome of the game that's implemented inside of the contract system on-chain. So one example of a game here that I have at the bottom is the exit challenge game in Plasma Cash, right? So if you have a Plasma Cash chain, and in that Plasma Cash chain, someone creates an invalid transaction, so you have a transaction where that transaction just got created out of nowhere and actually is a double spend, then, well, someone can go back and challenge and say, well, how about you give me the transaction that got spent by this thing? And the person attempting to fraudulently exit will not be able to respond to that challenge. So most of the activity here needs to happen, would only happen off-chain. The only thing that would happen on-chain is if some of the participants in the system disagree, then, well, they could end up sending a pile of messages onto the chain, and the chain would resolve them in some way. But the key thing is that you can send cheap, basically free off-chain transactions by sending these free off-chain messages that affect what the eventual outcome of the on-chain game would be. So, benefit is, first of all, you get some scaling because a lot of scaling because you reduce your use of the blockchain. Another benefit is that you increase privacy if done right. With these kinds of systems, basically anything that happens, any off-chain, any purely off-chain activity does not need to be seen by by anyone except for the participants in the game. And so you actually do a much better job of protecting privacy of your users if done right. Now, if done wrong, then you could potentially end up leaking data to a bunch of other people because of things like routing protocols. But that's a problem that has to be solved. One cost is that this increases the security assumptions of the blockchain that you're using. So you have to rely on the blockchain to not just not include invalid transactions, you have to rely on the blockchain to include valid transactions within some particular period of time. So it's not just a safety assumption, it's also a liveness assumption. And another cost is that users have the ability to kind of mildly attack each other. Basically, one user can force another user to get their assets locked up for some period of time. State channels. So state channels, basically the expected result of the on-chain game can change purely with off-chain messages. They're ideal for repeated interactions between participants. one benefit that you get is that this basically solves the latency issue, right? You get instant game theoretic finality. As soon as I sign the message and I send you the signed message, you know that if you really wanted to, you could take the signed message, broadcast it into the mechanism on the blockchain and get your money out. And so you could basically live as though you already have that money. Right? And in some game theoretic sense, you really do already have that money because you have the ability to get it if you wanted to. And this sort of change of the expected outcome, this change of the equilibrium of the game, happens purely as a result of off-chain messages, and so the payment itself does not need to wait for confirmations. Cost, capital inefficiency, cost, it's difficult to kind of change the set of participants. Plasma basically is a similar thing, except it gains a lot more power because you have an added ingredient, which is the ability to send small pieces of data onto the chain. And these small pieces are usually Merkle roots, and by submitting the Merkle root, you can basically change the ordering or you can commit to the ordering of large amounts of data. And so this is ideal for things like off-chain asset transfers. This is a really cool technology that you can use, for example, to make exchanges where the exchange does not have custody of the coins. So you can have a system where you have an exchange, and that exchange still manages the order book, and the exchange can still do things like processing a very large number of orders per second. But if the exchange gets hacked, the hacker cannot get anyone's coins. The only thing the hacker can do is basically force the exchange to shut down for a week. So, there are systems like that. Benefit, it's very flexible. Users can join and leave easily. But, the cost is that the finality needs to wait for a bit, and you don't have the same kind of censorship resistance against the plasma chain operator. So the point of all this, right, is that there is this kind of large set of designs that we could choose from if we want blockchains that are more efficient. We can use a combination of on-chain scalability improvements like sharding. We can use things like state channels. We can use things like plasma. And all of these technologies kind of find different corners and different positions in this complex kind of multi-dimensional and polyhedron of basically the trade-off curve, right? So in one position, you can get rid of the latency problems and you can have much higher efficiency in certain contexts at the cost of, losing some kinds of efficiency in other ways. There's another mechanism which lets you get higher scalability. It still has some latency, but you lose some of the censorship resistance. There's another mechanism which can preserve privacy, but it has other costs. You could even do things like, make all of your transactions on the blockchain encrypted with fancy zero-knowledge proofs. Then you gain, both strong guarantees of integrity and strong guarantees of privacy, but your million factor inefficiency balloons up to 100 million factor inefficiency, and 1,000 factor inefficiency would balloon up to 100,000 factor inefficiency. So, basically, if you want to design a blockchain application for your particular use case, then the first thing you want to start off is really figure out basically which of the core properties that you want, right? So, are you trying to make something which is guaranteed to stay online? Are you trying to make an application that can keep running independently of what some central operator does? Do you want to remove the need for a central operator? If you want to remove the need for a central operator, is it because you're afraid of the government, or is it just because you're lazy and you want to fire and forget and just build an application and not do anything anymore and let the community operate it? If you want to increase privacy, and what kind of privacy are you looking for? Do you care about privacy because you care about privacy? Do you care about privacy because you care about GDPR compliance? Do you care about privacy for some other reason? Do you care about latency, right? So there are applications where latency is very important. There are applications where latency is less important. And depending on all of these factors that affect your decision making, then you might either want to build something on a scalable blockchain, or you might want to build a plasma chain, or you might want to build a channel system. And if you use these technologies, then the trade-offs that were really serious problems with blockchain 1.0, so the million-factor efficiency loss, the fact that data is totally public, in the case of Bitcoin, the 10-minute block time, 1-hour confirmation time, all of these problems are really, really, really substantially alleviated, right? Like, we can create systems where, like, basically, if you're willing to make certain other compromises in other ways, including things like capital efficiency and including like sacrificing certain like specific guarantees in limited ways, we can create systems that are even within a factor of 10 of efficiency of centralized services. Like, we can create systems where, if you want to, like, it really does just start to make sense for existing centralized services, at least of some types, to start adopting these technologies. And like, that is like finding the right kind of part of the space for your application to be in, fully developing out all of the corners of the space, and making all of the corners of the space as easy to use, as easy to develop, and as easy to build things in, and really trying to figure out, well, how much can we really get? If we want it? Like, that's what I think the next phase of the crypto and blockchain space is about, and like, that phase has already begun. Thank you.